will graduate hopefully next Friday.
Hopefully.
And so now he's doing the dry run of his presentation. So, yeah.
Okay, I will present my thesis. The title of my thesis is Estimation of Ground Reaction Forces during running based on motion sensors and artificial neural networks. So, the summary of my presentation, we will start with the motivation, the state of the art, and the methodology, results, conclusion, and any future works. So, we will start to think about running. What is running? Running is we can say that running is a complex movement that involves a lot of part of our human body. So it is important to analyze the style of running, some key parameters of the running in order to improve the performance of in this case of athletes, and even for avoiding sport injuries. So here there is a list of some papers that are focusing on this field. So our challenge is, as I said before, improving the running performance and try to avoid sport injuries. The question is how, it is possible to develop an innovative system, and in the meantime has to be wearable, and the system has to give us the key metrics of the impact of the foot with the ground. And so far, the state of the art is the instrumented treadmill and the force platform. So we are able to measure, in that case, what we started is the ground reaction force. So these two tools are capable to measure the ground reaction forces easily. But the problem is that as you can see, these two tools are not wearable, and in the meantime are so expensive. So our challenge was to implement a system that is based on inertial measurement sensor, inertial measurement unit, and artificial neural network. And the combination of these two permits to give us an estimation of the ground reaction forces. So at the end, the advantages that we will have is for sure the low cost of the system, and wireless system, so it is wearable, and especially it is versatile, so we can use the system either in an indoor environment and in an outdoor environment. So here we can see how the system looks like. Just a simple system. We have two sensors, inertial sensors, that give us some inertial data as the acceleration and the gyroscope data. Everything is processed in the artificial neural network, and as the output we will have the ground reaction forces estimated. So we will go through the methodology. I will describe each step later on here with just a list. And so, just to start, we did the data collection using two inertial measurement units, namely the Actigraphs GT9X. And we attached these sensors in the two shanks of the subjects. Then afterwards, we proceed with the processing of the signals. Firstly, we carried out a stride segmentation. So we just identify the two instances of, the heel strike and the toe off, so the contact time. Then we proceed with the feature extraction. So we extracted some features from the data set. Then we generate realistic ground reaction force that are the target that the network will use to estimate the ground reaction force. And then finally we train and we test the neural network that we created. So just to say now, but I will, as I said before, I will explain this in details. We used an algorithm to implement and to develop and to validate our network, and this algorithm was the leave one subject out cross validation. So just to start the data collection, we had 10 participants, 7 males and 3 females. So here in this slide you can see the protocol. The subjects, firstly, they started to run on a treadmill for 1 minute at 8 kilometers per hour. Then they stop, and then we start to run for another minute at 10 kilometers per hour. Then they stop again, and then restart finally they start for the last time at another minute for 12 kilometers per hour. So here we can see all the different gyroscope data for the 3 different velocities. So the processing phase, we started with the stride segmentation. In the picture you can see how we segmented all the curve. So that's the gyroscope in the sagittal direction of the shank, and then we identify the heel strike and the tough instant. To identify these two moments, we just use an algorithm that was able to identify the two negative peaks of the curve. Just to say that it is worth to say that the two active graphs were automatically synchronized, so we didn't have any problem about the synchronization. Afterwards, we proceed with the feature extraction, and here is the list of the features that we extracted. So the normalized acceleration in all the three directions, the normalized radial velocity in all the three directions, then we differentiate all the acceleration in all the three directions, and then we computed the first and the double integral, so namely the velocity and the displacement of the acceleration in all the three directions. And then the sixth feature was the stance phase, so the contact time that we resampled between 1 and 100. Here's the clock method. So we will look at this because the main problem was that we didn't have available an instrumented treadmill or a force platform. So we used this method as a theoretical model that states that the ground reaction forces can be recreated just via the two force contributions. So as we can see here, there are two forces, impulses, J1 and J2. J1 is related to the mass 1 of the, as you can see in the picture, so the part of the lower part of the leg, so it corresponds to the 8% of the total mass. And then J2 is related to the rest of the body. Here we can see that the sum of the two impulses give us the shape, the curve of the total ground reaction force. And J2 and J1 are, just we can see here that depends on some parameters. For example, the body mass, the contact time, the flight time, and especially from these two factors, the delta T1, that is the time after the touchdown of the foot with the ground, and it corresponds to the time that the mass 1 reached zero, the vertical velocity 0. And then delta V1, that is the change of the velocity of the mass 1 during the delta T1. So it is worth to say that this method has been validated with an optoelectronic system, but not with inertial sensors. And so here we can see, just to clarify everything, we can see here two pictures that describe how the result of the Clark method. So on your right, on your left, we can see the acceleration in the sagittal axis, and we are able to recreate the ground reaction force that I assume that are the realistic one in the study. And so here we can see the two impulses that I mentioned before, the two contributions of the two impulses that give us the ground reaction force. So now we proceed to the artificial neural network. So what we did, we used several artificial neural networks. That all of them were composed by an input layer, 16 features, one hidden layer, and one output. All the activation function used in the hidden layer was a sigmoid function, and the one used in the output layer was a linear one. The learning algorithm that we used was a backpropagation algorithm. Just to give you some numbers, we trained every network for 2,000 iterations, and we used two stop conditions of the training approach. The first one was that if the gradient did not decrease for 6 consecutive iterations, the algorithm was stopped. And the second one was if the gradient was smaller than 10 to the -6, the algorithm was stopped. So here we can see more in details the Lee1 subject out cross validation. So what we did was to divide all the data set in n partition. N partition, the n was corresponding to the number of the subjects, so 10 parts. To partition at the beginning were temporarily removed because we use this for the final test. The reminders, so the 8 reminders, we consider one folder, one partition as the validation set, and the rest as the training set. At the end, we repeated this procedure for k times in order that every set is for one time the validation set. So at the end, we had an average error of the k folders. That's here we can see the validation, the results. So at the end, what we did was to test different neural networks that had different number of neurons in the hidden layer. So what we changed was the number of neurons, and we started to test network with just 5 neurons in the hidden layer until 100 neurons. So here in the table we can see all the different results in terms of mean absolute error and Pearson correlation coefficient. So at the end, the most performant topology was the network with 30 neurons in the hidden layer, because it was presenting the right compromise between the 2 outcome measures, so the mean absolute error and the correlation coefficient. And in the meantime, it was the right compromise even for the computational effort, so we've chosen this one. And here you can see the final result. So we used this network to test, we tested this network with the reminders, the 2 folders that we temporarily removed previously. And so here we can see the results. The blue curve is the target, so the target curve, so the curve that we created with the Clark method. And the orange one is the predicted. So we can see that here that the network is working really good. Just here to give you some numbers for the performance, here we can see in the table the performance of this network with 30 neurons. It's important to underline here that here we have another outcome measure, the mean absolute percentual error, and we have really a small percentage, so it means that we are able to predict in a very good way the curve. In the meantime, we have other 2 outcome measures, the peak estimation error, the mean estimation error, and also these 2 outcome measures have good results. So it means that we can give a good information about the maximal workload of the athletes, because we're able to predict the peak of every ground reaction force, and we're even able to give a good information about the average workload of the athletes, because we can see that the mean estimation error is just 8%. So the conclusion are, in this present study, what we did was to implement a new system that is based on motion sensors and artificial neural network, in conjunction with artificial neural network, and the result, as we can see, they are very promising. So it is a first step toward this kind of measuring ground reaction force that is an alternative way to measure. The future work, the possible future work, for sure improve overall performance of the algorithm. It is possible even to study the different performance of more artificial neural network structures. So for example, implementing another hidden layer, so see how the performance change with another hidden layer, or for example, adopting another activation function or a deep learning approach. So other things that we can change. And another way to improve everything is the feature selection. So adopting an algorithm of feature selection. So that means selecting the best features, the most discriminative features that can give us a better performance of the total system. And then it is so interesting even comparing this result with another system that use the ground reaction forces that are realistic. So from other tools like the force platform or the instrument travel. And that's it. Thanks for all.